We want to talk a little bit about phase diagrams, which are a tool that allow us to make predictions about what phases are preferred, how and when phase changes happen, and get some insight into what's going on with different compounds. So the phase diagram is a two-dimensional graph that describes what phases are present under certain conditions. So you'll see temperature is on the bottom, the horizontal axis, and pressure is on the vertical axis. And this is always going to be our standard kind of representation. So if we have, they're describing the external conditions. So if I have a temperature and a pressure, right, what conditions my substance is in, will that substance be a gas, a liquid, or a solid? And this general shape that we're seeing here is always going to generally be the case. It's always going to be solid over in the far right. We can see that corresponds to low temperatures, right? Generally, at low temperatures, we're always going to have the solid phase be present. Then we have liquid phase. Liquid phase is present at higher temperatures when the pressure is higher. And then finally, the gas phase is what dominates at higher temperatures and lower pressures. So we can understand these kind of patterns. Gases at high temperatures, molecules are moving fast. They tend to leave the liquid, leave the solid, move into the gas phase. At low ambient pressures as well, when we're down in kind of this territory on pressures, right? Remember, boiling is determined based on what the ambient pressure is. So when the pressure is really low, it's really easy to get a liquid to boil. So that's why the gas is dominant down here. So all of this region, anywhere down there, low pressures, high temperatures lead to gases. So this shape, this three-part shape, is generally going to be true. And they lead to certain assumptions. If you want to get something into a gas, decreasing the pressure and increasing the temperature will always work. Conversely, decreasing the temperature will always get you a solid. Eventually, at some point in time, you're going to hit solid. Increasing the pressure sometimes will work, usually, but we'll see about that. And so you'll see there's also, so that's overall what we're looking at, these kind of regions. We can also see that there are these lines that correspond to the changes, right? So they describe where you would phase change. And so, they describe then these sort of, if you think about it, you started here as a liquid. When you increase the temperature, eventually it'll become a gas. We call that boiling or vaporization. And so we can also see going the opposite direction would be condensation. Similarly, if you started with the liquid and you took at a constant temperature, you just decrease the pressure, eventually it will also vaporize. But when we have these lines right here, what those lines are then telling us is those are the combinations of temperature and pressure where the phase change happens. We call this idea as coexistence. You have both liquid and gas present at those temperatures. So under, say, atmospheric pressure, at 100 degrees Celsius, we think of water boiling. What that really means is at 100 degrees Celsius, you have both water and the gas present, right? The bubbles are literally forming inside the liquid. They eventually escape, and then more bubbles form to replace them. So you have both of them present. At 0 degrees Celsius, under ambient conditions, ambient pressure, you also have both liquid and solid. So they're both going to be present. So we have what's called coexistence along these conditions. You can also have coexistence between solid and gas, where we see the phase change of sublimation. We call this equilibrium. This is a word that we are going to see come back again and again throughout this semester. Equilibrium is the idea that you have both your reactants and your products, your starting and your endpoint, are both present at sort of equal amounts, okay? That you're doing this kind of move. And if you move off those conditions, you're going to favor one side. So if you under say atmospheric pressure, if you go to 101 Celsius, it's all gas. If you go to 99 Celsius, it's all liquid. There's that sweet spot right at 100 where you get that sort of balance. You get that mix of both. We call the fancy word is coexistence. They are living in harmony together, both the liquid and the gas. And so, one of the purposes of a phase diagram is to give you overall information. So the shape is useful. We can make predictions, but we can also start to see different we can predict where specific phase changes will happen. And there's also certain points of interest. One of them is the triple point. So the triple point is a pressure and temperature where all three phases coexist. So for example, for CO2, at negative 56.4 degrees Celsius and 5.11 atmospheres of pressure, you will have solid, liquid, and gas present. So it will look like you have a solid, you'll have like bubbles, like boiling solid, melting solid, all the kind of same thing, kind of a slushy, weird thing that comes into existence. One of the important points about the triple point is that is the lowest pressure where liquid can exist. So you'll note for CO2, that's 5 atmospheres. So liquid CO2 only exists above 5 atmospheres of pressure. That certainly exists. It's possible to do that in a lab, but it doesn't exist under ambient conditions. You'll note 1 atmosphere is where we live. That's why solid carbon dioxide sublimes. So the triple point is the maximum pressure for sublimation. So for water, that pressure is below 1 atmosphere. That's why we have liquid water at ambient conditions under that sort of 1 atmosphere of pressure that we live in. And so there's a couple other things. When we look at a phase diagram, we can make predictions as to what would happen if we were to change conditions. So we already kind of talked about this, that if you start, it is always true that if you have a liquid, if you increase the temperature or decrease the pressure, you're going to turn it into a gas. That is always true. And if you have a solid and you increase the temperature, it will always, depending on what the pressure is, if you're in a solid, increasing the temperature will turn it into a liquid or a gas. You will always, increasing the temperature always goes that way. We can also see effects of increasing pressure. This is water's phase diagram. So if you have gas, taking a gas and increasing the pressure on that gas, right, you're pushing those molecules together. They're going to go to either liquid or solid. But you'll note here, if I take, say, the solid, right here, if I have solid water and I increase the pressure on that water, it's going to turn into a liquid. My line's not the closest, but because there's a negative slope, it's curving to the right. If you increase the pressure on ice, it turns into liquid water. So for water, this is unique. Water is one of the only, a very, very, very small number of substances where increasing the pressure on the solid leads to melting. This is because solid ice has a lower density than liquid water. Increasing the pressure always leads to whatever the higher density phase is. That's solid for most things, but for water, liquid has a higher density. This is really important applications. This is why this, like when in cold wet, if you get to somewhere that's cold, the ponds and lakes don't entirely freeze. You only get ice on the top. That's important for the fish that live in those ponds, or the plants, or lizards or snakes that live in there. There's liquid water underneath the ice, and it stays liquid water because the ice starts to press in on it, and it will stop freezing. You have to get really cold to go all the way down. So that's really important and really useful. That's a very important property of water that makes it viable to live on Earth, especially in colder climates for water-based animals. But everything else, all other substances have a positive slope. So their line looks like this, where the increasing the in that case, increasing the pressure on the water would turn it into a solid. So that is generally true, but not the case for here. So that's for one of the reasons why we hypothesize that the middle of the Earth, like the middle of the Earth, is solid, because there's just so much pressure on it that it doesn't matter how hot it is. If you just keep increasing the pressure, you'll eventually turn it into a solid. So let's interpret our phase diagram. You'll note this is CO2 for the phase diagram. Again, this line is slanted to the right. That's what it looks like for most everything else besides water. So what is the phase of CO2 at 50 atmospheres and 0 degrees Celsius? All right, so that's going to be plotting basically where is that point on here. So you want to look at your axes. You'll see the temperatures. We got -56 and 31. So 0 is not on here. but we figured somewhere, I don't know, ballpark like here-ish. And then between 5 atmospheres and 73, we're given 5 and 73, so 50, I don't know, somewhere like here. And you'll note that puts us like somewhere like here-ish. So there's a liquid. So under these conditions, the purpose of a phase diagram is it tells me this right away. If I want to know if I'm at 50 atmospheres and 0 degrees Celsius, what are the conditions of CO2 going to be? It's going to be a liquid, right? I'm going to make CO2, and this is what I'm working in. I'm expecting it's going to be a liquid. And so I can make predictions about what it will look like. Conversely, if I want liquid CO2, what temperature, what pressure do I need to use? What happens when the pressure decreases to 1 atmosphere? Right? I can start to make predictions about, I know what the phase is under conditions. What happens if I change those conditions? So if I take this pressure, it was at 50 atmospheres, and I drop it down to 1 atmosphere, which is marked right there, I can see that now I'm going to be a gas. And what happens is I'm going to undergo a phase change, and that's called vaporization. Liquid to gas is called vaporization. So I'm undergoing a phase change into a gas where I'm seeing vaporization occur. So we can make predictions about how those changes will occur, what it will look like. So you kind of think, I'm going to decrease the pressure, what's going to happen? Or I want to turn it into a gas, how can I accomplish that? Participation 120, question 2. We're talking about this phase diagram over here, right? A, what phase is present at 5 atmospheres and 45 degrees Celsius? B, what phase change would occur if you decrease the pressure from point A? C, how could you change the temperature to cause the same phase change? So the phase change you identified in part B, how could you change the temperature for part A to cause the same phase change? This is the second question on participation 120, due Tuesday, January 20th at 11:59 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, for the phase diagram here, what phase is present at 5 atmospheres and 45 degrees Celsius? B, what phase change would occur if you decrease the pressure from 5 atmospheres and 45 degrees Celsius? And C, how could you change the temperature from 5 atmospheres and 45 degrees Celsius to cause the same phase change that you identified in part B? Okay, another question for participation 120. More videos to go. Might find some more questions for that participation assignment. Got to watch those videos and find out. See you there.